Financial models, chapter 5, section 7. So we're going to start going over some different models using exponential functions and logarithmic functions. And we're going to start with financial models. Future value formulas. Now, these are formulas that you would see when computing interest that you're either going to earn or interest that you're going to pay, depending on whether you're investing or borrowing money. The first one is the simple interest formula, which is where you pay interest strictly on what you're borrowing, or you're paid interest strictly on what you invested. So this is where if you invest $1,000 at 10% interest for 5 years, then each year you get paid 10% interest on that original $1,000. So you invested $1,000. The first year you make $100 interest. The second year you make $100 interest. The third year you make $100 interest. So that's why it's called the simple interest formula. You only pay or receive interest on the original amount borrowed or lent. And the formula for that is A, which A stands for future value, is equal to P, that's the principal or the present value, times 1 plus R, which is the interest rate written as a decimal, times T, the time. In general for us, that's in years. It is possible to use this formula in such a way that you do your time in terms of some other unit, but we use it as years. Beyond the simple interest formula, there's the compound interest formula. And this is where interest is compounded annually. So whereas simple interest, you only paid interest on that original amount, whatever was the principal. With compound interest, every time it's compounded or interest is computed, you not only pay interest on the principal, the original value, but you pay interest on any prior interest. So with my example of $1,000 as your principal and 10% interest rate, the first year interest would be $100, 10% of that 1,000. The next year you would take 10% of 1,100, the 1,000 plus the 100. Therefore, your interest would be $110. The next year would be the interest of your $1,210. So it'd be $121. So that's the way your interest gets compounded. So obviously compounding interest, you're going to end up paying more interest, or if it's an investment, you're going to be making more interest. And that's compounded annually. And this formula, future value A equal to the present value P times 1 plus R, the interest rate written as a decimal, all 1 plus R, the quantity raised to the T. So just be careful, that's not multiplying by T, that is raised to the T, that is an exponent. And you can go through and you can look online, you can see where this comes from, and you'll see that if you were to use the simple interest equation, but then start using the compound interest method of looking at the previous principal plus interest when you do it, that this formula builds out quickly and easily. But we've got it right here. Now, compounding one time a year is great, but that's not really how it's usually done. Some things will, but many times interest will be compounded a number of times per year, and we use N to indicate that number of times, and we're talking about regular intervals. What sometimes N is semi-annually. If it's semi-annually, that's 2 times per year. Quarterly, 4 times per year. Monthly, 12 times per year. Weekly, 52 times a year. Daily. Now be careful with this daily. You would think that would be 365 or 366, but in financial circles, when we talk about compounding daily, we generally use 360. So we assume that there are 12 30-day months. And how that affects compounding in the middle of the month gets a little exciting. not in the middle, but really at the end, that what happens is if you have a month with 31 days, then it compounds 30 days through in the month. The 31st day, it doesn't compound. So there's no interest charge. You have a month like February with 28 days. Well, then between the 28th and the 1st of March, it compounds two extra times. So just remember that when you're talking about daily, it's usually 360. And the formula for that, A is equal to P times 1 plus R over N raised to the NT. Now remember, N is the number of times compounding per year. So really what this is doing is it's taking the annual interest rate and dividing it by the number of times you're compounding. So if you have an annual interest rate and you're compounding monthly, take the annual interest rate, divide it by 12, and you actually get your monthly interest rate. If you take the time in years and you multiply it by N, that 12 in this case, then that tells you how many months it compounds. So effectively what this did was it changed your annual interest rate into an interest rate per compounding period, in this case a month, and it changed your time from being years to being number of months. So that's what this formula is really doing. So if you notice with this, if we compounded one time per year, if we were compounding annually, R divided by 1 is R. 1 times T is T. So the compound interest formula for compounding annually is just a special case of this compound interest formula for N times per year, where N is equal to 1. And then finally, what's really used, if you want to see how the bank does it, it's compound interest formula continuous. So basically, they compound interest continuously. Every second of every day, interest is compounding. And that formula is A is equal to P times E, remember the Euler constant, raised to the RT. And we'll take a look at all of these. So future value of an investment, you have $2,400 to invest at 4.2% interest. Determine how much money you will have after 3 years with each of the following: simple interest, interest compounded annually, interest compounded monthly, and interest compounded continuously. So this is going to be good because it's going to allow us to see the effect of compounding more frequently. So simple interest, obviously, since you only get interest on the original amount, that's going to be the lowest amount of money that you're going to make. So let's take a look at this. So we invest $2,400 at 4.2% for 3 years. So we were looking for simple interest, then A is equal to P times 1 plus RT. So we plug those in. Our principal was $2,400 that we invested. We invested it at 0.042 or 4.2% interest for 3 years. So we plug those values in and we come up with $2,702.40. And please be careful, order of operations, 0.042 times 3, then add 1, then take all of that and multiply it by 2,400. Okay, so you started with $2,400 and you ended up with $2,702.40. Now, I do want to point out that since we know what our principal payment was, the principal amount, that $2,400, that we can also determine how much interest we made. Right, so that would just be taking our future value, $2,702.40, and subtracting the $2,400, and we see, oh, we made $302.40 in interest. So that's how much we would have after 3 years with simple interest. Now, if we go to interest compounded annually, now our formula changed. A equals to P times 1 plus R raised to the T. And again, remember order of operations. So we plug in our principal value of 2,400, our interest rate of 4.2%, always as a decimal. Please keep that in mind. And T is 3 years. So we're going to take 1 plus 0.042. We're going to take that value and cube it. And then we're going to multiply that by 2,400. And we get $2,715.28. And as you can see, we made nearly $13 more in interest with compounding annually. Now, if we compound n times per year, and with this we'd said monthly, so n is equal to 12. So we're going to plug in the 2,400, the interest rate of 4.2% written as a decimal, divided by 12, which is the number of compoundings per year, and all of that raised to 12 times 3, the number of times compounded per year times the number of years, so the total number of compounding periods. And remember, order of operations again, 1 plus, we'll do the division first, 0.042 divided by 12, add 1. We had 12 times 3 in the exponent, so we're going to multiply that together, and then we're going to raise everything that was in the parentheses to that exponent, then multiply by 2,400. So we come out with $2,721.68. So again, we made another $6.40 in interest. So we're over $19 more interest by compounding monthly than we were by simple interest. But now you notice that as we increase the number of compoundings, the amount of interest increases. So what happens as we go to compounding continuously? Well, if you're compounding continuously, then you're constantly paying more interest or receiving more interest. In this case, it was an investment. So does that number go to infinity? And the answer is no. There is a limit in place. So you'll see that we actually will approach a value, and the continuous interest will show us what that value actually is. But if I went from 12 months to compounding weekly, we would see that the value that we would get for our future value would go up a little bit, but not very much. And as we go to compounding continuously, we see we've got our formula. A is equal to, I call it PERT, P times E to the RT. And we plug our values in here. Remember that E is approximately 2.71828, going on forever, never repeating, never ending. So I just put that in there with the dot and dot because you've got your calculator, which has the E button. So don't just approximate E. Use your calculator and let it approximate it as however many decimal places it does. So again, order of operations, make sure you multiply the exponent first, then take E to that power, then multiply by 2,400, and we see that we come out with $2,722.28. So with that, we gained what, 60 cents? So not much difference between compounding 12 times per year and compounding continuously. So we do have to remember that exponential functions do have their limits depending on how that's growing. So you're not going to come out with infinite interest. It does have its limitation. So let's continue on to effective rates of return. Now, when I talk about effective rates of return, let's just go back to that previous slide. Now, these were all the same interest rate, but depending on how we calculated that interest, whether it was simple interest, compounded annually, compounded monthly, compounded continuously, then we got different amounts of interest. So when we get to effective rates of return, what we're really looking at is a way to compare these interest rates. And the Truth in Lending Act of 1969 actually put into law that there had to be a standard way of presenting interest rates so that you could compare different types of interest, be it compound interest, be it simple interest, interest compounding continuously, other fees that come in. So they came up with effective rates, and many times we refer to those as effective annual yield or APR, the annual percentage rate. And anytime you take out a loan, they have to give you the APR. And that allows you to take a loan from one place and compare it to a loan from another place with all the things that they're including in. So we're going to look at effective rates of return. So the effective rate of interest R sub E, the sub E saying effective interest rate of an investment earning an annual interest rate R is given by, if it's compounding n times per year, R sub E is equal to 1 plus R over n raised to the n minus 1. Now you'll notice here there's no principal value involved. Also, you'll see that this formula looks very similar to our formula for future value when we were compounding n times per year. The difference being that we had A equal to P times 1 plus R over n, all raised to the NT. And we didn't have that minus 1 there. So basically, we've eliminated the number of years because we're looking at a single year here. And we eliminated the principal because the principal doesn't matter. We're looking at just the interest rate. So basically, we're basing on $1. If you invested $1, what would happen at the end of a year? What would be your interest? And if we look at this too, we see we now have, since it's $1, what are we doing? Well, we're dropping out that dollar at the end. So we're doing our calculation, getting our interest, and seeing what our future value is if we were to invest $1 for a year at this rate. And then we're subtracting that dollar out, so it's giving us our interest received, which becomes our interest rate since it's $1 for 1 year. So that's why it's very similar to that formula. And if we deal with continuous compounding, again, the principal disappears because we're just treating the principal as $1, and the time disappears because we're treating it as 1 year. So we have the same thing. R sub E is equal to E to the R minus 1. So as I said, APR, the annual percentage rate, the effective yield, which is usually done as a Y, that's really just the effective interest rate. You're offered a loan at 2.9% interest compounded weekly. What is the annual percentage rate of the loan? And let me just clarify one more thing. What we're doing with that is we're turning into 1 year, but we're really doing a comparison of if it was for 1 year, how does that compare to simple interest? So you're basically taking your compounded interest and saying, okay, let's make it act like simple interest. What would be the comparison? So you're offered this loan at 2.9% interest compounded weekly. Since it's compounded weekly, we're compounding 52 times a year. What is the annual percentage rate of the loan? Excuse me. So we start out with our formula, and notice I filled in APR for the effective rate because that's what we're looking for, is the APR is equal to 1 plus R over n raised to the n minus 1. So we just have, our interest rate is 2.9%. So R is going to be 0.029. We're compounding weekly, so n is going to be equal to 52. So we got 1 plus 0.029 over 52, all raised to the 52 minus 1. Order of operations, 0.029 divided by 52, then add 1, then raise that result to 52, then subtract 1. We come out with the APR equal to 0.0294, convert it back into a percent, and 2.94%. So you can see that even though you were offered a loan at 2.9%, your effective interest rate is actually 2.94%. Now, where this becomes important is you may be offered a loan by one place that gives you 2.9% interest compounded weekly. You may be offered a loan at another place that gives you 2.91%. So it's a higher interest rate, but compounded annually. And that may be a lower value in the end, even though it's a higher interest rate. Excuse me. So that's why it's important to do this, and it allows you to compare multiple loan offers with different interest rates and different compoundings and even different fees. Like I said, when you really get into this, they also take into account all the fees and everything that come into it to give you a fair comparison. Okay, so now to move on to the present value formulas. Our original formulas gave us the future value based on what you had started with. Present value formulas do the opposite. They say, okay, what do you want in the end? Let's find what you need to get there. So the present value P of A dollars to be received after T years, assuming a per annum interest rate R compounded N times per year, is you notice that when you have all variables in there that it gets really wordy and doesn't really tell you much. If you're compounding N times per year, P is equal to A times 1 plus R over N raised to the negative NT. Basically, all we did was we took the compounding N times per year formula and we solved it for P. So if you think about that, one of the first things you would have had to do to solve it for P is divide both sides by 1 plus R over N to the NT, which put it into the denominator or makes it to the negative NT. And that's all that happened here. We just divided it out, which put it on the other side with a negative exponent. Or if you're talking about continuous compounding, then the same thing, you divide both sides by e to the RT, and you get P is equal to A times e to the negative RT. So this becomes useful when you're trying to plan for the future. Knowing, hey, if I invest this much now, then in 20 years I'll have this much money is a great thing. But many times we know we need to have a certain amount of money, such as if you talk to a financial planner and you're trying to determine what you need to do to be able to retire and have a certain amount of funds available at that time so you can live for the rest of your life. Now, we're not going to get into the whole big thing of the calculations of annuities and stuff like that. So we're going to avoid that. But what financial planners do is they look at your situation now and say, okay, where do you want to be when you retire, however many years from now that is? And they determine how much money you need at that point to be able to live out the rest of your life and not have to worry about money. Then they say, okay, if you need this much money at that point to be able to live the rest of your life, what's it going to take to get you to that point in that amount of time? And that's really what we're doing here. We know at a certain time in the future, we want to have this much money available. How much do we need to invest now to be able to have that money then? So how much money do I need now? I will need $12,000 in 5 years. Who knows why? Maybe I'm planning on taking my wife on a cruise and I want to make sure that we have the money there to cover all the stuff. So I'm just planning ahead, $12,000. Or maybe I'm trying to put money aside because I'm going to buy my kid a used car one of my kids a used car in 5 years, or whatever the case may be. For some reason, I'm going to need $12,000 in 5 years. So how much do I need to invest now at 6.5% interest if it's continuously compounded? Okay, so continuous compounded puts us at P is equal to A times e to the negative RT. I start plugging in values. I need $12,000. The interest rate is 6.5%, so that's 0.065. Remember, always put it as a decimal. And we're talking about 5 years from now. So plugging those things in, remember, use your E key. So continuing on with our plugging in, so some intermediate values. It's good to practice these things and try it on your calculator and make sure you follow along. And we find out that at this point in time, we would need to invest $8,670.33. Now, in reality, this did not come out to be exactly $8,670.33. It came out to be $8,670, 32 point something or another cents. But since we want to make sure we have $12,000, we're going to round up our penny. If we round down, then we won't actually have $12,000. We're going to come out shy. So when you get to that penny, round it up, and that'll make sure, yeah, you're going to have slightly over $12,000. But I don't think you'll complain. The key is you need that amount of money. So there we go. So that covers financial models.